I'd like to introduce Cengiz Alaettinoglu, who will be presenting Can an Optical Channel Margins Help Alleviate Congestion at the IP Layer? Cengiz is a fellow at Siena and is coming to us from Los Angeles. This is Cengiz's 10th time presenting at NANOG. His first talk at NANOG was Routing Coordination Through the Internet Routing Registry at NANOG 13 in Dearborn, Michigan in 1998. Welcome back to NANOG, Cengiz. It's a pleasure to have you back.
Thank you, Chris. Well, for those of you who don't know me, I was actually with Packet Design, and you may have seen some of the demos of that software and Gear and so forth. But since then, we've been acquired by Siena, and then if you have ever heard me speak, it's usually about IP networks, MPLS, software control, traffic engineering, route analytics, it's all that stuff. I'm in the optical session, but I'm still talking about traffic engineering and software and automation and so forth. As a matter of fact, my first NANOG talk was about configuring BGP routers from routing registries, which is also automation software. So I haven't changed into 30 plus years. I'm still talking about the network automation. So we all know that as the distance increases, optical capacity, the line rate, decreases. And this is actually characterized by the Shannon channel capacity limit. The blue region in this graph actually shows all the pairs of viable distance and capacity combinations. And there's a mathematical equation that describes this region, and that's by this person, Shannon, and then this is called the Shannon channel capacity limit. So any point in this graph is actually viable. So if you overlay the standard Ethernet rates on top of this graph, which I did with the 100, 200, 400, and 800 gig regions, you have this gray section on top of the blue. And if you look at this curve, you can say, oh, there's a lot of blue which is not tapped. So can I actually use this capacity when I need it? For example, you may want a connection between two STI pairs, and distance may be little too long for 800 gig, but maybe you maybe do much better than the 400 gig. You may be able to actually support 600 gig between these two STI pairs. So I want to be able to tap into this region and then see what that how that helps in the IP layer. The other reason why we don't go all the way to the blue line in this distance and the capacity curve is the channel margin. So when you deploy a fiber and when you put the light through that fiber, initially if the fiber is new, the light doesn't have as much problem going to the other side of that fiber. There is still noise that happens along that fiber, but it's not like an old fiber that's been on the ground 10, 15 years. So when the optical networks are engineered, before you even put the fiber on the ground, before you actually have the optical network, you actually do this analytical, mathematical method, and then you actually figure out how much margin you need to reserve for the noise. Why do you need that? First of all, the fiber will age. You turn on a light, that light will be there for 10, 12 years. And then fiber will age and the noise will increase. Or it will be cut, then it will be repaired. And each of these, will increase the noise. And other lights will come onto the same fiber. Again, the noise will increase and so forth. So as a result, you need to leave some space for this margin. But as I said, you know all of this. What rate, what distance, how much margin, before you have a network. So coming from the IP world, this was like, wow. Because in the IP networks, we send packets, and without the network, there is no packets. And whereas all of this math, you can actually do in an optical network before you even deploy the network. So can we do better if we actually did it the IP way? What about if we actually collected telemetry from the network, and if it told us actual signal-to-noise ratios, and then we mine that data, analyze that data, and then figure out how much margin we should leave in this particular fiber? And the answer is yes. So basically to do that, you have to collect a whole bunch of telemetry from the optical network, mostly signal-to-noise ratios, bit error rates, latency, and so forth. You stream that from your optical devices. Then you know all of your service paths. An SDN controller obviously helps with that. And then you do the math, and then you figure out, hey, the maximum capacity this particular path can provide is 600 gigabit per second, and you have programmable coherent optics. You push this down, and now actually that particular path is supporting that particular rate. So this is actually definitely possible. We are more used to doing this kind of stuff in the IP network, but for the optical network, this is a little bit new. One word of caution, though, when you do this analysis, it's good for short to mid-term. It doesn't mean that particular signal-to-noise ratio will last 10, 12 years. So you can actually increase the capacity, but eventually you will have to decrease it because eventually the noise will increase. So it is actually useful for short to mid-term capacity. It's not for the long term. So, but if you have congestion in the IP network because you have a surge of traffic or you have multiple fiber cuts and then you have congestion, you can actually tap into the margins and increase the capacity of the links. That's actually possible. So two applications of this, which is quite easy to understand even for the IP people like me. One is the partial capacity restoration. So in the optical network, when a path is broken, we would like to restore it. I mean, it obviously depends on the service provider policies and so forth. But traditionally, we supported is a full capacity. In the network topology on the left, we have a working path, the home path, that's 2 hops. And then it supports 300 gigabit per second. And then, if that fiber is cut, and if you needed to restore that circuit, the next best path is 2 hops longer, and it can only support 250 gigabit per second. This is what we call partial capacity restoration. It's better than nothing, but it's not 300 gig. Traditionally, with the optical networks, if you did this, you had 2 choices. One is you say, I want 300 gig home path, no restoration path, because the rates do not match. Or you say, I want the home path, which is only 250 gig, restoration path 250 gig. So you couldn't really mismatch the rates. And there's a good reason for that. It's really the IP network above. It's not really about the optical network. So only way you can do this, basically the home and the restoration path different capacities, if you coordinated the optical network changes with the IP network. Because when this link comes up, it's going to come back at 250 gig. And then if the IP tries to put 300 gig of traffic on it, there's going to be packet drop. So you do need to coordinate the 2 layers. And that's really the gist of my talk. I'm really about coordinating the 2 layers. The second app is really looking at this SNR values end-to-end from AN to the ZN, the optical service paths. And then looking at how much noise is on that channel. And then you get a nice graph of green and red and so forth. If it is green, you can bump up the capacity of that signal. If it is red, that means, hey, there's going to be failure on this very soon. I mean, soon maybe 6 months or whatever, but there's going to be failure at some point. You may want to do a corrective action. Maybe there is a dirty fiber or bend someplace, or you just have to reduce the rate or something. But it tells you what is the current signal-to-noise ratio as opposed to what you planned in some mathematical model. And then you adjust that. But both of these can give you capacity when the IP network needs it. So can we tap into this at the IP network? So most IP networks actually will tolerate single fiber cut. Actually, we design it like that, right? I mean, we run most of the networks less than 50% utilizations. When we do that, basically, delay is more contained. We don't have to deal too much with the queuing delays and so forth. That means better user experience. And also, if there's a fiber cut, if there's a link failure, you have capacity elsewhere, right? Because you're only using 50% of your capacity. Other 50% can save you. Unfortunately, this is not always like this, because sometimes a fiber cut may bring up multiple IP links down, or you may have multiple unrelated fiber cuts and so forth. So from time to time, IP traffic engineering alone is not sufficient. You may need to actually tap into the optical network to help you. So in this talk, I'm going to go over 3 examples. In the first case, I'm going to focus on the partial capacity restoration. Yes, we want the full capacity restoration when it is possible, But that's not an interesting example for my talk, so I'll just talk about the partial capacity. Then I'm going to increase the capacity of an IP link, and then in the third case, I'm going to bring up a brand new IP link to the network, and then all of these three is again all about doing traffic engineering at the IP network. Let's say that you are running a worldwide network, and then your bottleneck, let's say, is through the Atlantic Ocean. You have North American traffic trying to go to Europe, European traffic going to North America, and you have two connections crossing the ocean, one between New York and London in the IP network, and then the other one is between Washington, D.C. and Paris. And for the sake of the example, let's say they are both 400 gigabits per second, and currently you split the traffic equally, 240 gigabits per second on each of these links, which gives you a really nicely, underutilized network, basically. And then let's say there is a fiber card in the middle of the ocean, and then you lose the New York to London link. What will happen in the IP network in this case? So basically, your IGP will converge, your RSVPTE, whatever, and then you basically end up sending all of the traffic on the other link. But that will adapt to 480 gigabits per second. Your capacity is 400. You are going to drop basically 80 gigabits per second traffic on this fiber, on this IP link. Not ideal, but that's what would happen if we just looked into IP network. So let's say that it's possible to restore this path between New York and London, but it's really long. Let's say it's going from New York to Montreal, to Iceland, to Oslo, to Sweden, to Finland, Denmark, and then eventually to London. But it's so long that you can only do 100 gigabits per second. And if you just did this, if you just bring this link up naively at the IP layer at the 100 gigabits per second, what will the IP network do? It will see link is up. It will go back to its routing, the default routing. It will actually again do 50-50 split, and it will actually send on this new link, on this newly brought up link, 240 gigabit per second traffic, and it will actually drop 140 gigabit per second of traffic. We actually made the network worse by bringing more capacity to the network because we did not coordinate it with the IP network. So as a result, actually, the network got worse. But the answer is easy. Basically, if you just run traffic engineering afterwards, you would realize that the capacity is now much less. You have to actually do unequal split between these two links. You put 96 gigabits per second on the first link and 384 on the other one, and you're not dropping packets anymore. And I really like this example because it illustrates that there is no solution if we just look at the IP network or if we just look at the optical network. But when you look at it holistically together, there is actually a working solution. This was the first example. In the second example, after the fiber cut, we have the congestion between the Washington and the Paris link, and we are dropping packets. Why not try to bring up the capacity of that? And you can actually look at the channel margin gauge and see what is the SNR values currently. If it allows it, you can bring it up at the 500 gigabit per second rate. You don't have to restore the other one. You can actually now, you're still not dropping. It's not ideal because very congested, but it's not dropping packets at least. The day is saved, and you can actually do this. But if you did this, you still have to run traffic engineering at the IP layer. Why? Because now you are dumping twice as much traffic to Paris, and behind Paris there's another IP network that may get congested. You need to make sure that portion of the network is handled as well. But there is another issue here, which is actually coming from the optical. So now we are changing the the spectrum of that light, and that's unfortunately is destructive. So you are going from 400 and 500 gig. It's incremental change of the spectrum. It's not like lasers are cold and they are warming up, but it will still take tens of seconds to actually do this. So as a result, this is costly, and you may want to do it if you know that you won't be able to restore that fiber for a week or two or something like that. And the second problem is you need additional IP router capacity. You need actually 500 gig instead of 400 gig, which is a standard Ethernet. For the time being, let's assume you have an available port someplace, and then you can do a lag and then add another 100 gig and then take advantage of that capacity. But that's actually an important piece of the puzzle. How do I find this additional router capacity? In the third case, in the third example, so the partial restoration path between New York to London was very long, right? And it actually, Montreal, Iceland, and Oslo. then rest of Europe all the way to London. What if we find a router port at Oslo and bring a new IP link to the network between New York and Oslo? So now the distance is much shorter, right? I mean, as a result, line rate that the optical network will support will be much higher. And as a matter of fact, for the sake of example, if it is 400 gigabits per second, you can do your 50-50 split, and then you bring the traffic to Oslo. You are still not done. You still have to run traffic engineering, because after Oslo, you may again create the congestion, right? Oslo may not have capacity in the IP network to actually go and then distribute this traffic to the rest of Europe. And for this case, it's a little more complicated than the case before. You also need an add-drop structure at Oslo so that you can take that optical signal and then bring it up to the IP network, and you need router ports as well. So how do you find these router ports? Actually, let's see how this system works. First, the most obvious part is that you need the topology. You need the IP topology, you need the optical topology, and you need this what we call the transitional links, the links that connect the optical network to the routed network. The one final component is the transitional link capacity flexibility. This actually tells you what race at the router port is available and what race at the optical, and what is the level of flexibility you have. For example, if you have Flex E, you can actually tune that. If you have the capability of OTM framing, you can actually pack OTUs inside OTUs and so forth, and you can actually get this rate as well. And then you can also do lags. All of this flexibility, what is available to you, is here. The second component is traffic metrics, and that's well understood by all of you guys. So basically, it's a demand on the IP network. And then finally, there is these policies, your policies. And in the policies, I think the most important one is the cost of change. So anytime you do something destructive, that's expensive. If you can solve this problem at the IP layer alone, that's free, right? So that has a cost of 0. If you need to do partial restoration, it's cheap, but it's not 0. If you need to do, the second example, it's more expensive. And the final example, maybe you only want to do it if it's a disaster recovery, because it's really expensive to actually, bring up a brand new IP link at the Oslo, because that may mean you may have to take that port from some other link, right? You may just say, oh, you run the optimization, and you say, hey, don't have that, Oslo to, I just embarrass myself for not knowing a second city in Sweden. But anyway, Oslo to some other place in Sweden, and take that port and then put it to this link, right? You have to come up with that. And then you run this optimization, and then result comes out. These are your new IP routes, these are your new optical service paths, and then you use an SDN controller and program the both layers of the network. The optimization is key here. You need to figure out what is the final solution, and also what resources you are swapping, right? There's no free bandwidth, right? You're taking something and you're putting it somewhere else. And then traditionally, when we talk about optimization, we are talking about network planning. So when we do network planning, it's for the next evolution of the network. You are going from 400 gig to 800 gig or something that you do once every few years, very slow human time scales. In those cases, when we do optimization, we can do K-cut analysis. We can do really global optimization that can take a week to run, but we don't care, because it's something you do once every few years, right? But the kind of optimization I'm talking about here is in the SDN controller. And you cannot take a day, because in one day, maybe you could have fixed that fiber. So it doesn't help you, right? You need to be faster, right? It's not obvious the IP 50 millisecond range, but you can have tens of seconds to minutes or whatever to run this optimization, which means you need to have heuristic algorithms, local searches, and so forth to find that port in Oslo. Anyway, once you run the optimization, it comes up with the solution, and then you deploy it. So takeaways from my talk: the optical networks have evolved. They are much more dynamic now. They have all of this telemetry that's available, and then you can actually mine it. You can actually figure out, for any given path in the optical network, what are the viable speed combinations, and whether you can borrow from the channel margins and so forth. And IP traffic engineering can take advantage of this new additional capacity. And traditionally, IP network is fine. It just runs, except, certain times, we have multiple fiber cuts, or, there's a new Fortnite release or something that you have congestion, then you can actually tap into this capacity as well. The big challenge is the third takeaway here. Basically, it's very difficult. IP network itself is very complex. I spent most of my career understanding it. Optical networks is extremely complex, but different people are looking into that, right? I've always, in my career, I always looked at IP networks. I kind of knew of the optical networks, but I know much more now after I started joining Siena, but my knowledge in optical networks is nothing, by comparison to my peers at Siena. So it's very difficult to have humans do this analysis and then come up with this. What does that mean? It means you have to have automation software deriving this. You need to have all of this analytics, machine learning, and SDN controller, mining this data, coming up with the solutions, and then showing it to the users, operators, and then once it is approved, it goes and deploys it. Thank you. Questions?
Hi, Eric Miller with Skywire Geekstream. This sounds very similar to what the FM radio industry went through when they did edge band subcarriers for the digital FM movement, where your normal channels were, so wide, but then you'd have small slices on the edge band. Is that what maybe? Was that what your motivation was to look for something like this?
Actually, I think it's exactly the same problem. You're absolutely right. It's spectrum, and then you have the noise, and then you don't want to create noise in somebody else's. It's exactly the same thing. I agree, but I don't think that was at least for me, because I'm not the guy behind the SNR mining and so forth. I'm more on the software of the automation of the two of them. Okay. I cannot speak for them, but I don't think it is their motivation. I don't think they might have. I just don't know. But I think it's the same problem.
And then a follow-up would be with perhaps a more precise edge band filter. Would you see there being a benefit in carving out a narrow band for a permanent additional channel to be used, say with a smaller 10 or 40 gig optic?
Yeah, if you have the capacity, absolutely. And then you can keep it longer or shorter. It's up to your policies, of course.
Yeah. Thank you.
Thank you.
Hi, Tony Tauber, Comcast. So has there been field trials of this kind of thing?
So there has been actually two that I know of. One is a North American service provider, and they actually do all three. In the third case, they use MEMS-based patch panel to even connect the ports to the routers and so forth. But I think they're pretty advanced, and they have their own research and their own SDN controller. They're not using our software. I cannot take credit for that, but definitely they are in the same boat with us. And there's been a trial in the European mobile operator as well. And in their case, it's actually the second use case that they actually wanted it.
Okay.
Thank you, thanks. Any other questions? Thank you.